Hi everyone. So this is in continuation with the previous problem, which is we were analyzing the pulse response of an inverting RC differentiator, and we just analyzed what happens to the circuit when you apply a step input, a positive step input. Since we are interested in finding what is the actual problem was to find what is the pulse response, we will now find out what happens to when the circuit encounters a negative edge or a negative step input. So first, again, I'm just telling all this because just to quickly refresh your memory, the op-amp is assumed to have a saturation voltages of plus minus 10. RC time constant of the the differentiator is 1 microsecond, and the DC gain is assumed to be 10 power 5. For our analysis, we will treat it almost like infinity. Okay, so when the rising edge, the first step, positive step input is applied to the capacitor, to this differentiator circuit, we said that the output is going to initially go to 0, initially start from 0, go to minus 10, which is minus Vsat. It will stay on for tau ln 2 seconds. Okay, this is the duration until which your inverting terminal actually jumps to plus the step voltage here, that is 10 volts. It happens to be 10 volts here, and the duration or the on time of this pulse is simply equal to the time it takes for this signal node voltage Vx to reach 0 volts. Okay, so usually it will go to minus Vsat. That's what its steady state will try to achieve, to go to minus Vsat. But when it reaches 0 itself, the circuit will more or less reach the steady state. So we found out that time happened to be, in this example, it turned out to be tau ln 2. Otherwise, you have to calculate it. Okay, if you know what is this step voltage, and you know this minus Vsat voltage, and you know the time constant, from that you can calculate what is the time it takes to reach 0 volts. So then that will give you the pulse width, the on time of this pulse, which will be tau ln 2. Then the pulse returns back to 0 and it stays at 0. Okay, so now for a very long time, see, if you see 1 millisecond is a very long time compared to see, this on time of the pulse is close to less than a microsecond. It is 0.693 microseconds. So as far as a 1 millisecond step is concerned, you can treat it like a step. You can treat it like a positive step and a negative step. This pulse signal can be treated like a positive step and a negative step. So at the end of 0.63 microseconds, the circuit reduces to something like this. The current in the resistor is 0. The op-amp is, the capacitor is charged to 10 volts. The op-amp's output is at 0 volts. The inverting node voltage is also at 0 volts. Okay, so this is the operating point of the circuit at this, for any time greater than tau ln 2, or the on time of the pulse. Now the actual action, that is a negative step, arrives at 1 millisecond. What happens to the circuit? The instant a negative step appears at the input of this differentiator, the capacitor will act like a short circuit. So this node voltage will go to 0. The capacitor voltage cannot change instantaneously. So what will happen? It will stay at 10 volts. It will keep the 10 volt across it. So the node voltage Vx was initially at 0. It will suddenly go to minus 10 volts. And this follows from the fact that the cap voltage cannot change instantaneously. Suddenly you have grounded one plate. So what will happen to the voltage at the other plate? It will go to minus 10 volts. So that the total voltage across the cap is plus 10 volts. So Vx suddenly drops from 0. It was at 0 for a long time. It dropped to minus 10 volts. Now when it reaches minus 10, you are now, remember here, the capacitor is offering a 0 impedance, incremental impedance, and so there is no negative feedback, and a huge input differential voltage is applied. So there is minus 10, so the output will go to plus 10. You applied a huge negative differential input voltage to the op-amp, so the output will go to plus 10 volts. So output initially was at 0, okay, it had gone through a small negative pulse, and then it had returned back to 0. Now at 1 millisecond, it will again go to plus 10 volts. So from then onwards, after that, once the output reaches plus 10 volts, since your differential input voltage is, in this case, it's going to be V plus minus V minus will be plus 10 volts. Your differential output voltage is much greater than 0. So your op-amp will be in saturation regime where your output is saturated. So op-amp is no longer in the it's no longer in the high gain mode. So you can replace the op-amp by a voltage source. Okay, here again I'm just reminding you again, we are replacing it by a voltage source because in our analysis we assumed an ideal op-amp can supply current even when the outputs are saturated. So I can treat it like an ideal voltage source. So now you have a circuit like this. An R, the only components that are active is a resistor, a capacitor, and the output of the op-amp. So the output of the op-amp, one end of the resistor is a 10 volt, capacitor is charged to, I've shown the direction in this way, let me put it this way, it is charged to plus 10 volts, and the other end of the resistor, the node voltage Vx is at minus 10 volts. So this node voltage is at minus 10 volts right now. Okay, so now what will be the steady state operating point for the circuit? The steady state for this RC circuit, not the operating point, the steady state for this circuit will be when the current in the circuit goes to 0, which means this node voltage Vx, now Vx of 1 millisecond is exactly equal to minus 10 volts. Vx of infinity will be plus 10 volts. So Vx is supposed to reach plus 10 volts. So this is how it will look like. Vx of t will start off at minus 10 volts at 1 milli, and then it will start charging to plus 10 volts. Okay, so as your Vx of t starts charging from minus 10, reaches 0 volts, the same thing will happen as what it happened for the rising edge case when a positive step input was applied. What will happen? When Vx of t becomes 0, what happens to the capacitor charge? This node voltage is at 0, the other end of the capacitor is 0 volts, the capacitor is discharged to 0 volts. There is no charge in the capacitor at this point. Okay, when a falling edge comes, once the Vx starts to charge to 10 volts, it's initially at minus 10, and when it goes to 0 volts, the voltage across the cap will be 0. All the charge that the cap had is lost now. Okay, resistor has discharged it. So the circuit will reduce to something like this. So your capacitor has 0 volts, 0 charge across it, Vx has come to 0 volts, V plus is at 0 volts, Vd is 0. Okay, if I and I can, the stable operating point for this circuit is when V0 also comes to 0. If V0 comes to 0, there will be no current in the resistor, and that's it. The circuit, none of the states, the voltages and currents in the circuit will no longer change, and a steady state has been achieved. So the output voltage initially was at 10 volts. In this entire duration, your Vx of t was always negative, which means your Vd, the input differential op-amp to the differential input to the op-amp, is always greater than 0. So it was justified to assume the output is 10 volts. The moment we reach this point, that is the point where your output, the Vx of t goes to 0, which happens to be at tau ln 2 seconds. At that instant, your op-amp starts coming into action. The op-amp's output voltage will start falling from plus 10, it will start going to minus 10, but when it reaches 0, the circuit will attain a steady state. I am not proving it using the op-amp's gain model, assuming the op-amp has a finite gain and all that, because we already did that for positive edge. The same thing will apply here as well. You can use a similar explanation here as well. But now you guys, because we have done the previous lecture, at this point you should be comfortable in knowing that if I apply a negative step, you should get a positive pulse at the output. The positive pulse, the peak value of the pulse will be equal to Vsat plus Vsat, and the on time of the pulse is usually given by the time taken for the node Vx, the inverting terminal, to reach 0 volts. Okay, so this is how it will look like: 1 millisecond to 1 milliseconds plus 0.693 microseconds. That will be the on time of this pulse. Okay, I've already shown where does this 0.693 come from. 0.693 is simply tau ln 2, and that comes from the time it takes for this node voltage Vx to reach from minus 10 to 0, which is the half value. Half value, the final value is plus 10. So the total delta V is 20. For the signal to go from minus 10 to 0, that's like half the change. Okay, half the total change in the voltage. So that happens to be tau ln 2 seconds. So if you plot this, so for this circuit, Now I'm in a position to plot the output waveform. If I feed a pulse input to this differentiator circuit, the output is going to look somewhat like this. It's going to look like a negative pulse at the rising edge and a positive pulse at the falling edge. This should make sense to you guys. The waveform shouldn't completely look alien to you because it's a differentiator at the end of the day. A differentiator should react only when there is sudden changes in the circuit, sudden changes in the input signal. Otherwise, when the input signal is flat for a very long time, here see this is a 1 millisecond is a very long duration compared to 0.693 micro. That's why I've shown it as this symbol to show that it's a very long time. So in this region, if you see the output is 0, the differentiator is not reacting to it. But the differentiator is producing a pulse. It's just generating a pulse whenever there is a transient event. Okay, when there is a transient event, so for a positive rising edge, you will produce a negative output, and for a negative or a falling edge, you will put the different. Since it's a different inverting differentiator, for a falling edge, it will produce a positive output. So that's how you interpret these outputs, and that's how this integrator will respond for a pulse input. Thank you.